We have a circle here. Let me mark the center of the circle as O. This is O, the center of the circle. Now, I'm going to highlight a piece of the circumference. A piece of the circumference is called an arc of the circle. So, I'm highlighting this piece and let me call it AB. This is the arc AB. If we let this arc AB to subtend an angle at the center, that is by joining A to O and by joining O and B. We have allowed AB, the arc, to subtend an angle at the center. This angle is popularly known as the central angle because it is subtended at the center. And the same arc, let us suppose that the same arc subtends another angle at any point on the circumference of the circle. So I am considering this point P. It can be anywhere. It could have been here, it could have been here, but just for convenience purposes, let me just start showing you with this point here, P. Now, by joining the end of this arc, the end point of the arc A to P, and joining the other end P and B. Yeah. And now I get one more angle APB. Angle AOB was the central angle. Angle AOB is the central angle. And now we have angle APB. This is popularly known as the inscribed angle. Because it's inscribed on the circumference of the circle, we call it the inscribed angle. Now you would have guessed it. What we are going to do here is to find the proof of the inscribed angle theorem. The theorem goes like this. The angle subtended by an arc at the center, that is the angle subtended by this angle AOB, is double that of the angle subtended by the same arc at any point on the circumference. So what we are going to prove here is the angle subtended at the center, angle AOB, is twice that of angle APB. This is the popular inscribed angle theorem, and let's try to prove it. Now for proving purposes, let me just connect P to O. This is after all the radius of the circle, and let me also extend this to make it the diameter of the circle. Now this P, and let me call this point as D. The line PD touches the ends of the circumference through the center of the circle, so it is the diameter of the circle. Now let us see what happens here. We have an isosceles triangle here. How do I say it's an isosceles triangle? I am talking about triangle AOP. Triangle AOP, we have OP and OA. Both of them are radii of the same circle. So, OP is equal to OA. So, this is an isosceles triangle since two of its sides are equal. And in an isosceles triangle, the angles opposite to the equal sides are also equal. Isn't it? Let me call these angles as A. If I call this A, this is also equal to A. So similarly, we'll consider the other triangle, triangle BOP. In triangle BOP, once again you have two radii. OP is equal to OB. And once again you have an isosceles triangle, and these two angles are the angles opposite to the equal sides are equal. Let me call them B. So this is also B, and this angle is also B. B denotes the measure of the angle. Right? Now what do we have here? What about this third angle in triangle AOP? We know that the sum of the angles in a triangle is 180 degrees. That is 2 times angle A plus angle AOP would be equal to 180 degrees. So can I say that angle AOP is equal to 180 minus 2A? And by the same explanation, I can also say that angle BOP is equal to 180 minus 2B. Now why are we doing all this? We have to find what is angle AOB. Right? Now what is angle AOB? Let me call this as C and this as D. So let me find in parts. What is angle C now? You know that this angle AOP is 180 minus 2A. Now angle C and angle AOP form a linear pair. Both of them add up to 180 degrees. So if angle AOP is this, then what is angle C? Angle C is equal to 2 times A. So I can write C as 2A, and by the same explanation, D would become equal to 2B. So what do we have here? Angle AOB is equal to 2A plus 2B. This is angle AOB. So if you want me to write it clearly, let me just shift a little down. Yeah. Angle AOB, the central angle, is equal to 2A plus 2B, or if I take 2 as common, it is 2 into A plus B, which is equal to, what is A plus B? Which is equal to 2 into angle APB, and this is what we had wanted to prove. The angle subtended by an arc at the center is double that of the angle subtended by it by any point on the circumference. Now we have taken the point here at P. It could be anywhere. So if this is the central angle at O, if this is the arc, P could have been here also. It could have been here. It could have been here. So let me just show you what would happen if P is here. It would be 2 times AOB. Now let me show let me call this P1 and let me call this P2. So what would have been the case if it was here? Again, the angle at P2 would be 2 times AOB. And this is the proof of the other theorem also. Angles in the same segment are equal. So the proof of this theorem, angles in the same segment are equal, comes from the inscribed angle theorem, because all these angles are equal to 2 angle AOB. And if P had been here, it's 2 angle AOB. And you can observe that all these are in the same segment, the major segment. These all the angles fall in the major segment. That is why we have angles in the same segment are equal. Now some other implications also follow from the inscribed angle theorem, which we would see in the upcoming video.